All right, let's dive into this really cool puzzle. How do you take a whole jumble of strings and sort them into their secret families? It's a classic programming challenge that seems pretty tricky at first, but you'll see it hides a really elegant solution. So take a look at these three strings. I mean, at first glance, they look totally different, right? But they actually share this hidden connection, a secret pattern that is the absolute key to solving this entire challenge. So here's our mission. We're given an array of strings just like this one, and we've got to group all the strings that belong to the same shifting sequence. Basically, we need to sort this jumble into nice, neat, related piles.
Okay, but before we can group them, we have to understand the rules of the game. What exactly makes these strings related to each other? What is a shifting sequence?
Well, the problem defines a shifting sequence as any group of strings where you can get from one to another just by shifting all the letters forward or backward in the alphabet. And, importantly, Z wraps right back around to A. So, for example, if you take ABC and you shift every single letter forward by one, you get BCD. Simple enough. Do it again, you get CDE. If you keep on going, you'll eventually hit XYZ. All of these strings, they're all part of the same family. Now, this seems pretty straightforward for a handful of strings, doesn't it? But what happens when we're dealing with hundreds of them, all with different lengths? The real challenge here isn't just grouping them, it's doing it efficiently. So how do we spot these family members quickly without having to do a ton of tedious one-by-one comparisons over and over again? A brute force approach, comparing every string to every other string is just way too slow. It's not going to work here. We need a much more clever, more elegant solution. So what's the secret? What's the trick? Well, it all comes down to finding a single, consistent identity for every member of a family, something we can call a canonical fingerprint. This one question right here is the key that unlocks the entire solution. Instead of comparing strings to each other, what if we could map every single string in a family to one single representative string? This fingerprint is going to be our canonical key. It's a standard form that every string in a sequence can be converted into. And the rule is simple. If two strings have the same fingerprint, they belong to the same family. That's it. Let's see it in action. Take the string BCD. Its first letter, B, is one step after A. So, to normalize it, we just shift every character back by one. And that gives us our fingerprint, ABC. And here's where the magic happens. Now take XYZ. The distance from X all the way back to A is 23 steps. So what happens if we shift all three letters back by 23? We also get ABC. They have the exact same fingerprint, which proves they belong together. So what if a string already starts with A, like as? Well, that's easy. Its fingerprint is just itself. The distance to shift is 0, so nothing changes at all. And this is just a brilliant illustration of how powerful this fingerprint idea is. For ba, we shift it back one position. The B becomes A, and the A wraps all the way around to Z. So the fingerprint is Oz, proving that ba and Oz are family. Okay, so let's get into the algorithm itself and see how this fingerprint idea helps us group all the strings really fast, using a super common data structure. The solution uses a hash map, which you can just think of like a dictionary. The key is going to be our unique fingerprint, and the value will be a list of all the original strings that share that exact same fingerprint. Let's walk through it. We start with a totally empty map. We grab the first string, ABC. Its fingerprint is, well, ABC. So we create a new group for it. Next up is ACF. Its fingerprint is ACF, so it gets its own new group too. Now things get interesting. We process BCD. We calculate its fingerprint, and it's ABC. So we just add BCD to that existing group. Then comes XYZ. Its key is also ABC, so it joins the same family. And then AZ starts a brand new group. And we just keep doing this for all the strings in our list. The string ba generates the key as, so it joins that group. A and Z both generate the key A, so they end up together. Once we've gone through the whole list, our hash map has all the families correctly sorted. So, you've learned to solve this specific problem. And that's awesome. But the underlying technique here, the pattern we used, is so much more valuable than just this one puzzle. This idea of grouping items by a canonical representation is an incredibly powerful pattern in programming. You can use the exact same logic to group anagrams, for instance, just by sorting their letters to create a fingerprint. It turns a really complex comparison problem into a super simple lookup.
You know, the big takeaway here is that transforming a problem by finding a simpler standard form is one of the most effective tools you have as a programmer. It really is all about finding that one true representation.
And this leaves us with a final thought. Now that you have this powerful pattern in your mind, what other messy, complex problems out there could be unlocked just by finding